A Honors Chemistry. It's Monday, April 20th, and they're going to do this day and tomorrow as well on rate law. Please turn to page 542. Make sure you got your calculator. Okay, sample problem B. You'll notice there's one reactant. Go to the next page. Sample problem C. You'll notice that there are two reactants. Back to sample problem B. We're going to calculate using some numbers today. 3 experiments, you can see number 1, number 2, number 3 in the table, have identical conditions. They were performed to measure the initial rate. Notice, initial rate of the reaction, because as a reaction proceeds, the rate will change. Concentrations will change, but in reality, we're just doing the initial rate. 2HI gas broke down, decomposed to hydrogen and iodine. Okay? The results are these. Do you notice in experiment 1, the concentration of hydrogen iodide in molarity is 0.015. And the rate at which the reaction progressed is 1.1 times 10 to the negative 3, or 0.0011. And what's the unit? Molarity per second. Change in molarity per second. That's the rate. All right. So now, because the reason there's a change in the reactant is because the reactant's getting used up. It's getting used up at that rate. 0.0011 molar used up per second. Okay, then experiment 2, they had a little higher concentration of HI, and they had a different higher rate at which it was being used up. And then the third one, a higher concentration and a higher rate. And so they want to write the rate law for the reaction. Well, there's only one reactant, HI, and so we're just going to go ahead and write the rate law like this. Constant, HI. What is that power going to be up there? What is the power going to be? I'll put a question mark right there. Well, let's find out. So let's do experiment 1 to experiment 2. Concentration versus the rate, say the new rate. Okay, between experiment 1 and 2. What happened to the concentration? Well, it went from 0.015 to 0.030. That sounds like it doubled. What happened to the rate? Well, it went from 1.1 times 10 to the negative 3 to 4.4 times 10 to the negative 3. That sounds like 4 times the amount of rate. You can take those two values and you can divide them with your calculator. First, the concentration doubled because 0.030 divided by 0.015 is 2. And 4.4 times 10 to the negative 3 divided by 1.1 times 10 to the negative 3 is 4. So when the concentration was doubled, the new rate was quadrupled. So let's go back to that rate law. When you double the concentration and the rate was quadrupled, what number do you have as a power that's going to give you 4? It's going to be a 2. It's going to, the rate law is this right here. Rate is a constant K, concentration of hydrogen iodide, gas squared. That, my dear, is the rate law. So let's say if you tripled the concentration, let's look at experiment 1 to experiment 3. Tripled. What happened to the new rate? 9.9 divided by 1.1. It is 9 times the rate. So when we triple the concentration, that's between experiment 1 and experiment 3. When we triple the concentration, do we get 9 times the rate? Is that what it said? So a triple, what gives me a 9? Answer, a triple squared. So the way you solve these in my estimation is you just simply write down concentration, new rate, and see what they're doing. When this doubles, that quadruples. And so you put a square there. When it triples, it's 9 times, so you put a square there. And so the rate law looks like this. R equals K, concentration AI, HI squared. Okay, let's go to the next one. Sample problem C, we got A plus B yields C. Those aren't even elements or compounds. That's a fictitious. We got reactant A reacting with B and giving you C. So let's see what's happening here. The conditions were identical in 3 experiments, except the concentration of the reactants was varied. So we got reactant A and we got reactant B. So the rate law is going to look like this. Constant, concentration of A, concentration of B. And it's going to be to some power. N and M. All right, so we're going to go ahead and figure out what those powers are, and then we'll have our rate law. So let's take from experiment 1 to experiment 2. We're going to hold one of those 2 reactants constant. And then we're going to look at the other reactant and see what it does to the rate. Let's not do 2 to 1. I mean 1 to 2. Let's do 2 to 1. Compare experiment 2 and experiment 1. We're going to hold one of them constant. So we're not going to look at it. And we're going to change the concentration of the other one and see what that does to the rate. Okay, what element, what reactant is being held constant between experiment 2 and experiment 1? 1.2 versus 1.2, A is constant. So we're not even going to look at A on this particular evaluation. What happens from experiment 2 to experiment 1 to B? The molarity goes from 1.2 to 2.4, so it doubles. And that is found by just simply taking 2.4 divided by 1.2, and you're going to get a doubling because we're going from 2 up to 1. Well, what happens to the rate? It goes from 4 up to 8. That also doubles. Okay, so what are you telling me? I'm telling you, just ignore the A and look at the B. If you double the B concentration, you're going to get a doubling of the rate. What power What power is going to cause that to happen? A 1. All right, so we've done that. Now let's go ahead and hold the other one constant. We're going to hold B constant. So we're going to ignore that as we go. Let's see, where is B constant? It looks like experiment 1 and experiment 3. So I'll tell you what. Why don't we go ahead and take a look at going from 1 to 3. B is constant, so we'll ignore it. We're only going to look at A. What happens to the concentration of A when you go from 1 to 3? Take 3.6 divided by 1.2. Is it triple? 3.6 divided by 1.2, it tripled. And going from 1 to 3, what happened to the rate? We're going to have to take 7.2 times 10 to the negative 7 and divide it by 8 times 10 to the negative 8. And when you do that, you're going to get 9 times the rate. So the question is, just ignore this. We've already got that figured out. So let's figure out what the power is for this one. Ignore that one. And so if we triple the concentration, it gives us 9 times the rate. Triple what gives us 9? The answer is 2. 3 squared is 9. It is. Now, I'm going to have to go ahead and calculate the value of K. Once again, this is going to be a little bit longer of a lesson. I'm sorry. This is just the way it is. So the rate law is K, concentration of A squared, concentration of B to the first power. First, solve for K. We want the value of K. So divide both sides by K. No, don't do that. Divide both sides by A, concentration of A squared, concentration of B to the first power. Okay, and when you do that, you'll have K by itself. So I'm going to go ahead and just say, I'm going to put K over here because I like reading from left to right. Okay, now pick any one of those experiments you want. It doesn't matter. Let's do experiment 1. The concentration of A was 1.2 molar. And the don't forget to square it, part of the rate law. And the concentration of B was 2.4 molar in experiment 1. And then the rate on experiment 1 was 8.0 times 10 to the negative 8. And it is called molarity per second. Now, what you're going to do is you're going to see that 8 times 10 to the negative 8, we're just doing the numbers, divided by 1.2, further divided by 2.4, or divided by the product of 1.2 times 2.4 enclosed in parentheses. Either way, when you do all of that, you're going to get a number of 2.3 times 10 to the 8 But the question is, what are the units? Well, can you see molarity in the numerator? Can you see molarity squared times molarity in the denominator? What is molarity over molarity cubed? Isn't that equal to molarity squared in the denominator, which we call molarity to the -2 because it's in the denominator? Now, when you take a fraction over a fraction, right? This is a denominator thing. Okay? And that's the way it is. You know, a fraction over a fraction, 1 over 2 over 3 over 4. What do? You flip the bottom and you multiply. And so what do you do here? That seconds is in the denominator. Ends up being in the denominator. And so what you do is you flip that there would be a 1 up here and be molarity cubed down there. And it would be molarity cubed down there. And so you're going to get molarity cubed, and that molarity makes it molarity squared. And then it's molarity squared seconds in the denominator. And that's the way we do it mathematically, annotated. Isn't that fun? I'm going to give you a couple of those to try.